Very exciting times in this field. We're lucky to have someone as knowledgeable and distinguished as Ravi to tell us about the technical and commercial challenges of the networks, of which there are many. So thank you very much, Ravi, and let's go ahead and get started then.
Thank you, Alison. Thank you for inviting me here. My name is Ravi Puvvala. I'm the founder and CEO of Savari. The topic today is technical and commercial challenges of V2V and V2I networks. A brief background about our company. We are the experts in the V2X domain. We have developed an automotive-grade connected vehicle platform, mainly focusing on safety and mobility applications. We have rival a lot of our competition in terms of our outdoor performance, both within the onboard and the roadside units. We are powered by Qualcomm and Intel chipsets. We are part of various trials that are happening within the country in Arizona, California, Michigan, Minneapolis, and New York. We are developing these technologies by simultaneously working with 8 automotive manufacturers, and our company got selected for the US DOT's biggest trial that just started a couple of months ago in Ann Arbor, Michigan. And I'll talk to you briefly about some of the things. I've divided my presentation into kind of like 3 areas. I wasn't sure in terms of how much background and exposure you had in this area. The first part focuses on technology. What is the underlying technology behind this? The second part focuses on the commercial and the technical challenges that are there in this domain, and the third part talks briefly about the testbeds and what's going on in the different parts of the world. Okay. If you have any questions, please feel free to interrupt me anytime, because this is very informal discussion, and the whole idea is to convey what's happening in this domain. And I personally have been working in this area for the past 8 years. I've done a lot of work with automotive OEMs. I've been working with the U.S. government on their various projects and trials that they're doing. This is a very interesting area, and to me, it definitely establishes the foundation that people are going to see in the future autonomous vehicles. So start with the definition of what is V2V and V2I, the vehicle to infrastructure and vehicle to vehicle. There are a lot of questions about what is a connected vehicle platform, and how what we are doing is different to a standard telematics unit. We focus on mainly in terms of bringing smart information from outside of the vehicle into the vehicle, right? That is our definition of V2X networks. So if I'm driving on a road, if there's a pedestrian on the road that's on my path, I would like to be warned so that I can make intelligent decisions. If there's another vehicle that's potentially part of my path, it could potentially cause an accident, I would like to be aware of it. So what we call as situational awareness, that is coming from the infrastructure or other vehicles, to enable 3 different types of areas, which is building safety applications, building mobility applications, and building environmental type of applications, but primarily using information that's coming both from the infrastructure and other vehicles. Okay. The underlying technology behind a lot of this is called DSRC, stands for Dedicated Short Range Communications. For any communications to work, you have to have a spectrum. The spectrum has to be has to have certain characteristics in terms of enabling people to develop applications that are that have very low latency. Typically when you're developing safety applications, the driver has about 3 seconds to react. So you want to make sure that the situation has been detected and given enough warning to the driver so that he can make a corrective action. Whether the vehicle can take a corrective action by itself, it depends on the maturity of the technology and how it's getting integrated into the vehicle. Okay. There are a lot of other characteristics with this spectrum. To me, this is one of the primary reasons of why this technology is getting more popular, and also what type of exposure that the automotive companies, the tier 1 suppliers, and system suppliers like us are able to provide. Okay. Spectrum has about 75 megahertz of bandwidth. It's part of the 5.9 gigahertz band, which is very adjacent to the unlicensed 5.8 Wi-Fi band. The primary goal that we've chosen this application is because it can provide low latency, high reliability, and interoperability, security, and privacy are one of the primary aspects of any standard to make it interoperable with other car manufacturers. So, which is why whatever underlying technology is being used, it has to be adapted across the world, whether it's US, Europe, Australia, or in Asia. I'll kind of go through some of the aspects of where the spectrum is allocated and how different countries are using it. Yeah.
Low latency in real world. What do you mean by?
Hang on just a second.
Yeah.
Give me this microphone.
Quick question about low latency in real world. When you say you have low latency and two vehicles are communicating, so what do
we consider as low latency? It's less than 100 milliseconds in terms of being able to. If you look at the definition of these technology, it's short messages. Okay, and in terms of people have compared why don't we use LTE or Wi-Fi or Bluetooth to enable similar mechanisms. And there is a good slide that's available on the US DOT website which talks about what type of latencies are associated with each with each popular technology, right? This is the only band or the technology that's out there that meets the current safety requirements and other applications that we are trying to build.
Okay, thanks.
So intention of this standard is to build, as I talked about, the vehicle safety, emergency vehicle notification, and also help people to be notified when they're stuck in a traffic congestion, because we can provide real-time traffic data using such technology. It all depends on how these vehicle information is connected to the web and how that information is transmitted back to the user, whether it's coming from the infrastructure or coming from the other vehicle. So there are not much of connotations about what we do in the mobility area, but more focus on the safety domain, and which is what I will explain in the coming slides. This is the worldwide spectrum that I was talking about, how it has been allocated in different parts of the world, Europe and North America and Japan. As you could see, there are certain channelization differentiations between Europe and North America. The one on the green, the 5.875 to 5.905 in Europe, and whereas in North America it's 5.850 to 5.925. So Europe has a narrowed bandwidth. Japan has their technology allocated in the 700 megahertz band, and there are certain other variations in terms of the actual channelization, whether when it's compared to Australia, Singapore. I wasn't aware of the activities that are happening in Russia, but potentially they're all around the same spectrum band. To us, it took us about 10 years of standardization activities to ensure that everybody is convinced that that is the band to use. And that's why I think this technology that's based on this 5.9 gigahertz band is very critical, right? You need to have a licensed band. You need to have prioritization of the messages, especially when you are trying to build safety applications. We need to have a right of way to make sure that the vehicles are only the ones which are able to communicate in that particular band. Today there have been some efforts that are going on with companies who are trying to figure out a way to use the spectrum for other purposes. If you kind of Google, about some of the spectrum activities that are happening in the 5.9 gigahertz band, you could see some of the big companies who want to use 5.9 gigahertz band for other, probably like gigabit wireless or other needs that might be useful, that might utilize this particular spectrum. Okay. As far as the global standards between US and Europe, The underlying IEEE standard is what we call as 802.11p. It stands for Wireless Access for Vehicular Environments. The 11p is the main PHY and the MAC layer. It's kind of a MAC 1.5 layer. And the Europe has what's called as an ITS G5 specification, which is very close to the IEEE 802.11p. By the way, all these slides are going to be online, so don't have to worry about everything will be posted. So when we go to the next layer about the PHY and the MAC, there is the IEEE 609 stack, which defines what type of network layers mechanism we could use and how do we control the MAC layer. So there are different variations between the .1 talks about the applications, the 609.2 talks about the security, and the .3 talks about the network layer, whether it is IPv4 or IPv6. Or typically we have only IPv6 and what we call as the wave short message protocol. These are the only two mechanisms that are available in the US standards to be able to transmit messages at the network layer. When it comes to the application layer, we use the Society of Automotive Engineers standards called SAE J2735, which defines all the messages that are going out on the air. And Europe has a similar mechanisms called CAM and DENIM. CAM stands for I think content awareness messages, and I think the DENIM stands for some sort of a emergency notification mechanism. Okay, so what I think all the suppliers like us are doing is to build hardware platforms that meets both the US and the European standards. So you have a unique platform that car manufacturers can choose, whether it is the European OEM or the US OEM. Okay. The connector, yeah, go ahead.
In US, is this determined by NIST, National Institute of Standard Technology?
Do me a favor, Hugo, and repeat it.
Sorry. Is this standard, is this band or this specification is approved by NIST?
So IEEE defines what the different layers of the standards.
Okay.
What happens is the automotive manufacturers, they come up with a minimum performance requirement standard that is also part of the Society of Automotive Engineers, and they define which portions of the IEEE standards that they would choose to make it part of the connected vehicle technology. Okay, and similar consortiums and automotive groups that exist throughout Europe as well, and they decide as a consortium what sort of the specifications become part of the connected vehicle or V2X networks.
Okay, I mean international level, is there national body to?
So if you look at the regulation that happened in the past 20-30 years, we have a great representation from the US government. Ed, he works for Federal Highway Authority.
Purely in an unofficial capacity.
Okay. All right, Ed, sorry.
This is being recorded.
Sure. Okay. The US government has a body called NHTSA, National Highway Traffic Safety Administration. They decide in terms of what type of technology would go into the vehicle. So, for example, if you look at the past history of seat belts, that was mandated by NHTSA, NHTSA, and ACC, Adaptive Cruise Control, was mandated by NHTSA. Right. So there are a lot of emergency brake control, adaptive cruise control, and even this. There is a roadmap in terms of when this technology could be potentially be mandated, and the current date that the U.S. government is looking at to make a decision whether to mandate or not to mandate would be about August 2013 timeframe. That's just a decision to go ahead and come up with the policy mechanisms. Then they have to do a safety and benefit analysis, and based on the safety benefit analysis report, and they would come back with a recommendation.
Okay, thanks.
So there's a lot of, yeah, go ahead.
You just mentioned that the automobile that will get the minimum range or something, and then by the spectrum of the signal, also they have some effective range. What about that? I mean,
how much range do they expect? So part of the minimum requirement is that the technology should be able to communicate within 300 meters in any direction. The research is divided into, the application part is divided into three areas: the mobility, environmental applications, and the safety applications. So the dynamic mobility applications are the ones which are aimed at improving, decision-making capabilities for people who are maintaining the road infrastructure, the traffic engineers, right? How do we get the traffic data? Let's say, for example, the timing of a traffic light to the driver, or the timing of the traffic light to the vehicle, or coming up with a mechanism to coordinate, a multiple traffic light multiple intersections, so that they could be actuated depending on the flow of the traffic. This could also act as a virtual detector. So when a vehicle comes by to a traffic light today, we have a magnetic detector that's underlying the road, and that's how a vehicle is detected, and the traffic light controller activates the next phase of the signal. And today we don't have to rely on this kind of magnetic detectors, but these messages could go to the infrastructure and enable traffic lights to perform more optimally. Okay, so that's what falls under the dynamic mobility applications. Environmental applications are, we use this for determining whether a particular portion of the road has bad weather, or if we want to warn the driver that there is a pending storm that's coming through and they have to drive carefully, or if some road accident or a work zone activity that's happening, that we want to inform the driver, right? And we can also coming up with mechanisms about what sort of emissions that are being performed by the vehicle, and that could be reported to the infrastructure to make sure that they conform to the EPA standards. So there's a lot of research going on in this area, and there's a lot of work that is being funded to develop more and more environmental applications. Okay. Yeah, go ahead.
What is the public
Hang on
transit?
just a second.
How does that play in this?
Sure.
I think I may have shouted out one.
So the transit, there are a lot of things. It's a very broad area. Okay. One example is, the goal of this whole research that's being funded by the government. They want more people to use the transit buses, right? Or transit vehicles, whatever that mode of transportation might be. So what type of information do they need from the real-time traffic infrastructure, so that they could tell the driver while they're driving, say, if you get off the highway right now, you can reach your destination probably much faster than you still continue to drive to your final destination. That's one mechanism, right? Second is, if some people want to have drive it in a fuel efficient way, we can come up with mechanisms to reroute them. So there's a lot of back-end data collection and reporting back to the driver that's going on, that's pertain to this area. So what happens is, this information at the back end is dependent on what data is being generated by each vehicle, and that's how it gets collated in a central database and then notified back to the end mechanism. Today, a lot of these, we don't have cars that are sending messages constantly, right? By enabling each car to send messages out constantly, that's what's called as a probes. Today we have probes on cell phones, we have probes on telematics hardware platforms. This is another way of generating the probe messages, through this SAE J2735 type of messages that are going out from the vehicle on this particular specified band, that could be collected to enable people to ride transit modes of transportation. So the US DOT website has a lot more details about many of these areas. This is just a glimpse of what type of applications that can be developed. And the safety applications, this is where our company focuses a lot by working with the automotive OEMs. The mechanisms that we do is, for example, when two cars have mechanisms to talk to each other, instead of the emergency brake light, the visual inspection, we can send a message to the driver, to the vehicle at the back, saying that the brake has been applied. The second type of application is what we call as a forward collision warning. So if we believe that you are currently driving at a higher speed than the driver in the front, and if you continue to drive at the same speed, you would be notified that there will be a potential forward collision warning. A lot of these applications, I would show a video which details a lot more in detail. It's very amazing video. You could see these applications working in action. Okay. After just 2 more slides, I finish my technology background, and then I'll show the video. That will give you a very good glimpse of what's happening. Yeah, go ahead.
So what about the backbone infrastructure, the backhaul for this?
Okay.
Will you be talking maybe in the
No, I mean not much, because the backhaul infrastructure, there are certain things that the government is doing and how they collect and how they disseminate the information. Today they do that for weather data. There are a lot of mechanisms in terms of they do have a global database. There are a lot of traffic databases that are also available based on the sensor information that's coming from different modes of mechanisms. I don't think there is a single method or mode that the government has decided to, disseminate. I think it's probably up to the private industry to figure out how to use this information and then send information back to the, consumers. This technology only enables people to come up with a mechanism. It doesn't define a specific model that needs to be used for any type of these applications. Okay. Yeah, the whole goal of the safety using DSRC is to have the vehicles to talk to each other or constantly sending messages, what we call as a basic safety message. That is the message, it's about 48 bytes, which would go out from each vehicle. The basic safety message would have information, your speed, your location coordinates. It has information about where you are coming from, not about the addresses. The GPS coordinates, the history of the GPS coordinates, what we call as a path history, and it also tells you the future of the the GPS path. And the video talks a bit more about these applications and the background behind it. Okay. The vehicle to infrastructure using DSRC, what we do is the roadside unit. The role of the roadside unit is to send out what we call as a map message. It is the intersection map information, and also what we call as a signal phase and timing of the traffic controller to the vehicles. And the roadside unit is also responsible to receive basic safety messages from vehicles. And what enables this is to have a two-way communication between the vehicle and the infrastructure. Okay. So for example, if there's a transit vehicle or an emergency vehicle going on, it can send a priority message to the traffic controller that to extend a green phase, or it could tell well ahead that I want to make sure that these set of traffic lights that are coming down the road should be all green because an ambulance needs to go through that particular roadway. So a lot of these mechanisms are enabled, and we do actually deploy some of these applications in one of the test beds in the country. So there are multiple applications that are being defined as we speak and being demonstrated and validated in various parts of the country. Right? Transit signal priority, what we just talked about, sending a priority message from the emergency vehicles to the infrastructure. Right? Preemption mechanisms in terms of making sure that the emergency vehicles get the priorities or the work zone alerts. The infrastructure can send a message to the consumer saying that there is a work zone, you have to reduce your driving speed. It also can send out travel information messages. It's basically, a lot of these things can be done from a centralized cloud server. What a roadside unit does is to be able to have a mechanism to send out more real-time information. I think our belief is that when you make it all centralized and trying to, a lot of these could be probably potentially be programmed, but we want to have a standard mechanism of communication from the infrastructure to the to the vehicle. Okay. So when a mandate happens and every vehicle would have a 5.9 gigahertz radio, this information would be much more easier to be provided. Right. The question is about how long does this mandate take, or what is the role of penetration for this technology among all the vehicles. Right. So I'll briefly stop here and kind of go through the video. Oh, okay. We'll see how it goes. No, it's connected.
Imagine a day when vehicles are able to communicate with one another. Imagine a future where drivers would be warned of a potential crash by the vehicle they're driving because of this communication. The technology to make this happen exists today, and future possibilities are just around the corner.
Continuing to build on the positive results of previous crash avoidance safety system programs, the United States Department of Transportation, working cooperatively with 8 major automotive manufacturers, Ford, General Motors, Honda, Hyundai Kia, Mercedes-Benz, Nissan, Toyota, and Volkswagen Audi, initiated a vehicle-to-vehicle, V2V for short, collaborative project, where one of the objectives is to determine if a diverse group of drivers accept V2V safety technology and to see how they respond to the system.
What makes V2V communication work is a wireless protocol similar to Wi-Fi called Dedicated Short-Range Communications, or DSRC for short. When DSRC is combined with GPS technology, the result is a low-cost V2V communication system that provides a 360-degree view of similarly equipped vehicles within communication range.
Transmitted messages common to all vehicles include each vehicle's current GPS position, vehicle speed, acceleration, and heading. Vehicle control information such as the transmission state, brake status, and steering wheel angle, as well as the vehicle's path history and path prediction.
Path history is a set of previous positions which provide a history of where a vehicle has been. It represents about 300 meters of the vehicle's past path of travel. Only the points necessary to define its path history are transmitted. When a vehicle is driving down a straight road, for example, only a few data points are needed to represent its path history. When that same vehicle enters a curve or set of curves, more data points are needed to represent its path history.
Path prediction allows a vehicle to provide its future trajectory and its confidence in this trajectory. The confidence will tend to be high on straight roadways or curves with a constant curvature, and lower during lane changes or transitions in and out of curves.
With path history and path prediction, the vehicle is essentially being provided with a dynamic map of the roadway geometry ahead, essential information for performing threat assessment and predicting potential crashes.
It's important to note that information transmitted by every vehicle is anonymous and does not include any personally identifying information such as name or license plate number. And a sophisticated security system has been put in place to ensure that all information exchanged between vehicles is authentic and can be trusted.
By employing common data, security, and communication standards, V2V interoperability among automotive manufacturers has been achieved.
Since all vehicles communicate in the same way, each automotive manufacturer is free to develop their own safety applications and warning indicators.
When a crash is predicted, the vehicle will provide a warning to the driver, either through a seat vibration, tone, or visual display, or combinations of these indicators.
The systems developed under this project are only intended to provide crash warnings. The driver remains in control at all times, and the vehicle will not automatically brake or steer.
The following scenarios demonstrate some of the safety applications that can be enabled using V2V technology. The Emergency Electronic Brake Light Safety Application, or EEBL, can notify a driver of a hard braking vehicle in the path ahead. 3 vehicles are traveling in the same lane. You are driving the last vehicle. You can't see the first vehicle because it's being blocked by the vehicle directly in front of you. Unexpectedly, the first vehicle slams on its brakes. Because of V2V communication, your vehicle is able to provide a warning of the hard braking vehicle ahead, well before you see brake lights from the vehicle directly in front of you. This warning will enable you to drive safely and avoid a potential crash.
The Blind Spot Warning Safety Application, or BSW, lets a driver know that there's a vehicle that may not be visible positioned in the driver's blind spot. Because of V2V communication, a blind spot advisory is issued to make you aware of the presence of this vehicle. Should you attempt a lane change with the vehicle still in your blind spot, this advisory will escalate to a warning, letting you know that it is not safe to change lanes.
The Lane Change Warning, or LCW, is a safety application intended to provide a warning if a driver intends to change lanes into a zone that will soon be occupied by a faster-moving vehicle traveling in the same direction. Using the data obtained through V2V communication, your vehicle predicts that this vehicle will soon be in this zone. If you attempt to make a lane change, a warning will be provided, letting you know that the lane change should not be attempted.
The Forward Collision Warning Application, or FCW, is intended to warn the driver of a potential rear-end crash with a stopped or slower-moving vehicle ahead. You are driving over a small hill, and ahead in your lane is a slower-moving vehicle. The vehicle ahead is wirelessly sending its information, allowing your vehicle to provide a warning if you are approaching too quickly and are in a potential rear-end crash situation. This will enable you to slow to a safe speed and distance behind the slower-moving vehicle.
Now consider that a vehicle ahead of you has, for example, run out of gas and is stopped in your lane. The vehicle directly in front of you makes a late lane change around the stopped vehicle. Even though you can't see the stopped vehicle, because of V2V communication, your vehicle is aware of the stopped vehicle and provides you with a warning ahead of time so that you can safely slow your vehicle before reaching the stopped vehicle ahead.
The Do Not Pass Warning, or DNPW, is a safety application intended to let the driver know that it is not safe to attempt to pass a slower-moving vehicle because of oncoming traffic in the passing zone. Using V2V communication, your vehicle is continually looking for cars in your intended passing zone. If a vehicle is detected in the passing zone, a driver advisory is provided, letting you know that the passing situation is potentially unsafe. Should you attempt to pass the slower vehicle, the advisory escalates to a warning, so you can stop the attempted maneuver and remain in your lane.
The Intersection Movement Assist, or IMA, is a safety application intended to warn the driver when it is not safe to enter an intersection because of the high likelihood of a crash with a vehicle on an adjacent approach to the same intersection from either the left or the right. If an intersecting vehicle is detected using V2V communication, a driver warning is provided if it is unsafe for you to enter the intersection.
Now, imagine you are approaching an intersection where you have the right-of-way and cross-traffic must stop. As you approach the intersection, the driver of a crossing vehicle fails to stop and continues traveling through the intersection directly in front of you. A warning is provided when the violating cross-traffic is detected. This helps you respond in a timely manner and stop rather than continuing through the intersection and potentially getting into a crash.
The Left Turn Assist application, or LTA, is intended to warn the driver when making a left turn that it may not be safe to proceed because of oncoming traffic. You are approaching an intersection and get into the left turn lane prior to making a left-hand turn at the intersection. As you release the brakes to continue through the turn, thinking the path is clear, a warning is provided indicating that oncoming traffic has been detected using V2V communication and it is not safe to complete the turn.
Caution, oncoming vehicle.
When the oncoming traffic clears, the warning goes away and the left turn can be completed. The safety applications and scenarios you have just seen are but a glimpse into the future of what may be possible when all vehicles can communicate and understand one another, regardless of make, model, or manufacturer.
Several challenges remain, but the U.S. DOT and auto manufacturers continue their commitment to further the development of V2V safety technology. Technology that will prove beneficial to all of the drivers of our roads the world over, for today, tomorrow, and generations to come.
On behalf of the U.S. Department of Transportation and the CAMP VSC3 Consortium, we wish you safe driving.
Yeah. If the message that the cops car is sending, as we talked about, it's,
What will happen is the cops will lay a backpack in the corner and it'll always say that.
That's a good one.
Just like the cardboard ones on the way up to Reno. This would be,
Yeah.
looks like it can cause some kind of deadlock situation for a short period of time, and everybody is over aware and everybody starts slowing the vehicle.
I mean, if there's a false message that comes through,
No, even for the genuine message,
Uh-huh. I mean, I think if you look at the current active safety domain, today people use radars and cameras, right? What we believe is using this technology, we can avoid 98% of the accidents, okay? So it's accident prevention and, how to warn the driver when something bad is going to happen to them. How they react, what it means to the congestion, we have to really see in real life world, right? We can't really predict that. Yeah, you could be right. People could be overreacting it, my guess is in the future, they're probably semi-autonomous, not full autonomous, that just like the way, ABS system works, that things would be taken control. Yeah, go ahead. Video available? This is not our video, it's a government video, but I think there shouldn't be any problem. I don't have a copy of that video that I don't have the rights to, distribute it. But, it's fine, I don't see anything copyrighted in there. I'll let you guys know whether there is a public video available. Yeah. Yeah, I think the question was whether the LTA application would be, the warning would be ignored by the consumers. So that's why there is a lot of driver acceptance. These applications are built. As you see in the video, everything is live, right? Everything is working. Everything is fully integrated into the vehicles, and these are taken from real applications and real scenarios. So there's a lot of acceptance criteria that NHTSA is very strict about anything related to safety. So each application would go through millions of scenarios before it actually gets integrated into the actual vehicle. So there is also a lot of user acceptance criteria that applications. The question about the false alerts and things, whether the consumer would ignore it, today it probably happens through radars and cameras too, but I'm not sure about the percentage of the false alerts coming between radars and cameras versus V2V systems.
If you record this information, if accident happens, then basically this information can be used by insurance companies?
The question is, can this information be used by the insurance companies? That is part of the policy that the government is evaluating, what can be and cannot be used. I don't think there is any decision that has been made in terms of, whether this portion of the information can be contributed towards it. I think that's a regulatory and a policy decision that is part of the decision-making process. So there is no decision one way or the other. That's what the government is evaluating. Yeah.
Does the same thing apply to like the CHP sitting on the corner with the receiver and saying, "Gosh, you're going 83 miles an hour"?
Yeah, I think the question is, can a CHP, California Highway Patrol, can use these messages and then, because it tells you the speed, can they give you a ticket based on that? I think it's no different than, that is also part of the policy decisions that is going to go through, the regulation. I think if we enforce it in a way that people, find it annoying or they would probably want to find ways to turn it off or cut it off, right? So it all depends on, this is part of the, it's not just the technology, the policy decisions in terms of lot goes on within the NHTSA and other bodies in terms of how they would mandate something like this and what constitutes as, valid information that can be recorded or, be used against the driver in many types of scenarios, right? So this is all part of the policy making decision that would go through. Yeah, I don't think there's, yeah.
My other kind of unrelated question was, with a 300-meter range, how do you do pass warning with like 70 mile an hour on a two-lane road in the middle of nowhere? I would think I'd need like maybe a mile. Please repeat the question.
Yeah, I think the question was, is 300-meter range sufficient, for a car that's coming at 70 miles an hour through an intersection? This is why I told you about the 3-second warning, and this is exactly why the technology that underlying technology we are using is very, very low latency, because it all has to happen in real time. Anything beyond that, we really cannot determine how the technology would work or if we can guarantee some of these latencies.
My question was this, so this system will work if all the vehicles have this working.
Right.
If some vehicles don't have it working, right, and people might thinking, oh, I will get a warning, but they may not get a warning, right? So
Yeah, the question was whether when drivers get used to this type of warnings, do they expect the penetration? Does every car need to have this technology, or is this going to work with only, like, say, 10% of the vehicles in the United States embedded with such technology? That's a $1 million question. Very good question, right? If you think about it, the way I see it, how it gets integrated, I don't think this technology would go on its own. Today, it has to be embedded with existing driver assistance systems like radars and cameras, because what it does, it enhances an existing ADAS platform to with V2V messages. So you take a radar-based warning mechanism, right? Radars, there are front radars, there are radars for different types of applications. It's a forward collision warning application. So FCW application that is working using radars will be enhanced with V2V information. So at some point in the future, when we don't know what type of penetration rate that needs to exist, that we can develop this application without the use of radars. But in the meantime, until there is enough penetration, it has to be embedded with an existing ADAS platform. Yes.
So on that same note, I mean, if you're driving a brand new car, you're going to get all these marvelous warnings, unless I'm coming at you with my very old car. Is there sort of a minimum level of play, which basically says I have a box that transmits, even though I get none of the data back from it?
Very good. Yeah. Right. The question was, what happens when the new vehicle is equipped with this latest and the greatest technology, but I have an old vehicle, what sort of technology needs to be embedded? I'll go through some of this, what we are doing in some of the trials here. So we have 3 different classes of devices. What we call as a vehicle awareness device, that's a very dumb device, only it sends out the basic safety message, but doesn't feed back anything to the driver. So when any mandate that happens, that is kind of the minimum technology that they expect to embed in every car. Old car, new car, doesn't matter, right? Just like your beep beep box, that's what will get integrated, and that would be the most inexpensive platform. There are certain target rate, the target price targets that the government is looking at to make sure this technology can be easily integrated. But right, every existing vehicle, there are 200 million vehicles today in the country, right? All these vehicles have to be integrated with certain minimum technology so that each car is able to send this message.
Just the way cars alone or all the vehicles?
Well, when I say cars, I meant all types of modes of transportation, whether it is transit bus, yeah.
Is this an open standard that any company can adopt, or are there any licensing or IP issues?
The question was, is this an open standard? Are there any IP issues? I think everything is standards based. I don't think there is anything related to proprietary technology here. It can be easily, and I think there are certain government bodies looking at making it part of the open source and making it more available to the community. Definitely, yeah. There is no proprietary technology here. Yeah, go ahead.
How are you handling the balance between latency and security?
The question was, how do we handle the balance between the latency and the security? Today, the mode of definition of security in the US and Europe, is a little different. The current US security is based on the public key infrastructure. So we expect the car to preload it with certain number of certificates. And each message is secured using a certificate that's time bound. So let's say, for example, 5 a.m. to 5:05 a.m. There's a particular set of certificate that we would use. How we would need to get the information back to the consumer or the driver is when there is a bad actor. And that's what we are determining in terms of what would be the right mode of communication to make sure that we notify every device of the bad actors. So, but in order for the applications to work and the technology to work, there is no third-party mechanism that exists to validate that the messages are secured. Okay.
What is the required GPS accuracy?
Okay, the question was about GPS accuracy. So that's kind of what I'm going to talk about, on my technical challenges slide. If you see here, what I have is 4 areas of the technical challenges. What I call as the radio. What sort of technical challenges do we have to make this technology to work? We briefly talked about the spectrum mechanism, right? We also talked about, what happens if there are 600 vehicles on a given intersection, is this technology scalable to make sure that the messages go through, right? and the positioning issues with the positioning in terms of what sort of accuracy do we require. We require sub-meter level accuracy, right? Do we need to have any other modes of mechanism to improve? Absolutely. The more accuracy that we have, better it is, right? But the question is, can we achieve high accuracy GPS using low cost GPS receivers? That is the challenge that we are facing in terms of how do we meet the price targets and achieve the GPS accuracy that is required by these applications. The third challenge that we have is the security, right? How do we get these certificates loaded onto these vehicles, and how do we ensure that we have a mechanism to communicate back to the device so that we can notify of the bad actors, and we can reload the new certificates and things. So this whole certificate management systems in the back end is a big challenge in terms of who maintains it, how is it going to be allocated, and all these, what is the cost associated to create a back end CMS mechanism, who has the authority, does the government have the authority, does the OEM has the authority, the car manufacturer, so all these things are being determined as we speak. Okay. I'll talk briefly about the congestion control, right? So we're kind of developing algorithms mainly on two things, that transmit, the control that transmit power and control the data rate at which these messages are going out with certain set of probabilistic approach, right? We use common things like packet error rate, inter-packet gap, and how busy is the channel to determine how these messages go out. Okay, so we have a lot of testing that we are doing throughout the country. There's a test that's we just did some tests in Alameda. There's a old abandoned military track there. We did a test with 200 cars. It's actually with 100 vehicles. And we did a test with 200 vehicles in a research center in Marysville, Ohio. Your question? It's like question.
Was it on the Autobahn?
Oh, Autobahn. The question was about where did the testing in Germany happen? They do have a test track. I don't know if it is part of the Autobahn or not. There are a couple of tier 1 suppliers who are part of it's a consortium. It's called SimTD. You probably can Google it, and then it's somewhere in Munich or Frankfurt. Yeah, question.
As far as I know, it's in Munich and urban area. It's not
Okay. Yeah, it's not. It is in the urban area, as he's saying. Yeah, it's definitely not simulated, but what we use sometimes is a race car track to do a lot of this testing. And there are some testing that happens in the urban areas, but that's just mainly used for data collection. We don't go and simulate a lot of these application scenarios that we just showed with the real cars. I mean, with cars that are being used for these purposes of testing. So, yeah, question. See, I don't think there's anything that can be done to prevent it. If there is a jamming, if somebody comes and jams the channel, it only blocks that particular area of mechanism. There could be certain provisions in the law when the mandate happens on how somebody could be prevented, that a jammer cannot do this. It's not legal to do this, right? But I don't think there's any technology thing that we could do, any radio mechanism that we can avoid somebody not to jam, right? So it's a policy mechanism. Yeah.
So the vehicle unit, is it having any link to the car electronics, or it is just a standalone unit?
Okay, the question was whether this onboard unit is linked to the OBD2 port or the CAN bus of the vehicle. If you want accurate data, and we have different classes of devices, and one of the classes of devices does require connectivity to the CAN bus or the OBD2 port. These applications will still work even if it is not connected, because bear in mind that we are not taking control of the vehicle. We are only providing the information. In the absence of connectivity to the car, the data bus of the car, we use the GPS information that's part of the onboard unit. So they would still work. They would work better if we are connected to the car, but it's not that this technology is absolutely dependent on it. Yeah, question. The question was related to what is that power consumed by the radios. And the second question was, what is the cost of these onboard units in volume? I think the question of the power consumption, it's, the specification talks about that you can use up to 36 dB. It's much higher than your unlicensed band, right? You could come up with 1 watt radio, 2 watt radios, depends on how you design your radios and, how you would achieve this 300 meter range. So, in terms of the cost is based on, the volume. It's what the price would be. It's at anybody's guess. It depends on how it's getting integrated with other ADAS systems, or is it a standalone mechanism, or is it like, it could be as cheap as $50, or it could be as expensive as, $1,000. It all depends on, who is manufacturing it, how does it get integrated. So you can make it as cheap as possible. You can make it as expensive as, as the, depending on the technology and things. Yeah. So some of the other questions, I'll try to kind of, go through these other remaining slides pretty quickly. The positioning requirements is mainly to determine about, which road and which lane, the vehicle is in, to be able to make these applications work better. On the security side, yeah, question?
I just noted that you're saying 90% confidence. I'm wondering, like, close enough, you were near close enough to actually be safe.
Question was, is 90% confidence good enough for these applications to work? Yes. This is kind of the minimum requirement, right? It depends on, obviously, the higher the confidence level, the better judgment that we could make. So there are a lot of other things that we take into consideration, not just the accuracy. It also depends on the relative accuracy of the, the GPS systems. It's not like about absolute accuracy that we care about. I don't think there is technology that's there at very low cost where we can build these applications based on absolute accuracy of the GPS system. So, if both people are equally bad, it works very well. That question. Yeah, I mean, I can finish this, and then I know we're kind of like, I'm sorry that I'm taking a little more time. The security domain, as we briefly talked about, we have the certificate, what we call as the CRL, which is certificate revocation list, and we have a certification authority. And the way we solve this problem is, we don't go and verify every message. We only verify messages that really cause an alert to the driver. That's what we call as verify and demand. So, the certificates are, we have short-term certificates and fallback certificates to ensure that the onboard device is able to function at any given point of time. And we get this pool of certificates, and the certification revocation list is maintained by a back-end authority, and which gets communicated to the, the onboard device. Verify and demand is what we talked about, how to avoid validating every message that's coming from the other vehicle. The connectivity with the certificate authority, there are various mechanisms that are available using 3G, Wi-Fi. We can use the same DSRC radio to connect to the infrastructure, to be able to connect to the certificate authority, to ensure that we can download the certificates, we can get the updated revocation list, and there are a lot of mechanisms available how we can maintain this connectivity using a telematics platform, using your smartphone. Choices are umpteen, right? We briefly talked about the certificate management systems, who maintains them, is it the collaboration between the OEM vehicle, automotive manufacturers, and, the main issue here is how do we ensure the consumer that their information is protected and then their privacy is not compromised, that there is no single government body or automotive manufacturer can determine or, provide, details about what the driver, whether the certificate is coming to, you as a consumer. Okay. It's kind of the big picture of the technical solutions, in the three main areas as I talk about: communications, positioning, and security. You need to have a flexible spectrum, a radio, sort of like a software-defined radio that can tune to the various spectrum changes that are required for various parts of the world. You need to have good control of the, transmit power and the rate, to ensure that we can solve the congestion issue. The positioning issue, we talked about that, the receivers have to have sub-meter level of accuracy, and the security mechanisms, it needs to be more things like verify and demand, so that You don't need to have a very expensive onboard unit platform, to validate every message that's going on the air. So some of the business challenges that we have is there's a decision. This is mainly focused on the U.S. market. Europe has, as Alison mentioned, that 2015 timeline. They have a different focus between U.S. and Europe. U.S. mainly focuses on safety applications to deploy this technology, whereas Europe focuses mainly on mobility applications to deploy this technology. So that's a key difference. The way this technology gets penetrated into the market is through aftermarket channels. I believe that the long-term trends, depending on how well LTE and Wi-Fi gets penetrated into the consumer vehicles, and obviously the demand by the consumer to have this technology integrated, right? The U.S. mandate decision to 2013, Europe 2015, both have different focuses in terms of how they see this technology being deployed and being mandated. We looked at different deployment channels, whether it's aftermarket, fleet owners. What are the possible areas where we can start deploying these technologies? Potentially at the airports, through the insurance industry. There are a lot of channels that we are exploring in terms of enabling this technology through existing devices. So if you look at the infrastructure alone, we have 350,000 signalized intersections in the US. So AASHTO, which stands for American Association for Highways State Transportation Officials. So they have plans to deploy this infrastructure by 2020 and 2030. You can see their roadmaps in terms of how long they think or what sort of money that they anticipate that they would require to enable 350,000 intersections with this technology, right? Whether it happens by 2020, 2030, we have to wait and see. In Europe, selected areas like big cities, there's no need to cover the entire continent. It all depends on what type of V2I applications that the government wants to first deploy, right? I'll briefly talk about the safety pilot. This is the activity that's happening in Ann Arbor, which just started. You can Google for US DOT safety pilot. This is the biggest deployment that's happening out there. The results of this particular trial feeds into the 2013 decision the NHTSA, the National Highway Transportation Safety Administration, would mandate. It involves 3,000 volunteer vehicles. We are enabling the technology in all these 3,000 vehicles, and they collect the data, and this data is what is used to determine the benefits of this technology, right? This is the global deployments. All the yellow dots represent the activities that are happening currently. The Michigan, California, we have activities in Arizona. There are tests that are currently happening in Germany, various parts of Europe actually. There are some activities that started happening in China. Singapore just started an activity with their tolling operations, and there is also a trial that's happening in Australia as well. So this is the trial that's happening in Ann Arbor, Michigan. It has about 75 miles of instrumented roadway. There are about 30 traffic light intersections where we have provided the hardware to enable V2I applications, and we have 3,000 different types of vehicles, whether it's cars, trucks, and buses that are embedded with this technology. And this is mainly conducted by University of Michigan Transportation Research Institute. It's called UMTRI. This map, the blue dots and the yellow dots represents where these roadside units are deployed. This is the university area. So what they did was the University of Michigan, Ann Arbor, is the test conductor. So they went around, talked to all the different PTA associations, and said they would give them, certain compensation for them to try this technology out, and the money would go to the schools. Now they have about 3,000 volunteers, and these volunteers are regular drivers. I mean, parents, people who are dropping their kids. They're chosen based on their driving patterns, whether they're able to hit these different blue dots. And some of the vehicles are instrumented with both radars and cameras, as well as this V2V technology, so that they could compare the alerts that are coming from different types of mechanisms. Is a radar able to generate the alert? Is a V2V system able to generate the alert? And they have data acquisition systems that are integrated into these vehicles, which are used to compare one technology versus the other. So there's a lot of instrumentation that has happened, and this trial just started in August. So it's going to go on for a year, and that's what would feed into the decision-making process. And there are different stages. The yellow is the stage 1 roadside units, the blue is the stage 2 roadside units, and the purple is where the UMTRI's main location is, where everybody goes. They have a garage there. All the volunteer vehicles, they go there and they get equipped with this technology, and they go back and doing what they're supposed to do. Yeah. Yeah. Okay. So basically what it is, as I talked about how this technology gets integrated, if we are able to sell it through Fry's, Best Buys, we call it an aftermarket, same exact hardware platform. If the car manufacturer integrates it as part of a new vehicle, it's called the integrated system because it's done by the automotive manufacturer like General Motors or Ford. If it is retrofitted by a dealer, we call it as a retrofitted device because you have to walk into the dealer and they would do a much better job of where this device gets installed. So it's just the installation mechanisms and what type of package that exists for the same technology. Because the retrofit mechanism could be embedded with something else. The in-vehicular integrated system is probably embedded with some more hardcore safety. So it's just different ways of ensuring this technology gets into older vehicles, new vehicles, or even things like trucks and buses. And I briefly talked about the vehicle awareness device, which is what the dumb device that just generates the basic safety messages. As I talked about the development and the trends, the way we see this technology gets integrated is by integrating with ADAS, aftermarket, advanced driver assistance systems. Like today, they are based on cameras and radars. More radio penetration helps us to ensure that this technology can be easily enabled. There are a lot of other mechanisms like electric vehicles, mileage-based user fee. There are a lot of other V2I type of applications that are being deployed which can make use of this technology. So today, the current state of the world is only 2% of the vehicles are connected. So there's a lot of market. So what's coming tomorrow? I'm just done with this. This is my last slide. What's coming tomorrow is the combination of these autonomous and connected vehicles, right? I don't know if you can see. The green is the short-range radars, and the blue is the ultrasonic sensors. So this is what is equipped, and what you see in the middle is the digital, the dedicated short-range communications with the GPS integrated for V2V systems. And this is the Google car, which is currently integrated with these radars and cameras. But today, if we enable this technology, you can do autonomous driving without, very expensive radars and cameras. And that's what we see as coming tomorrow. Yep, that's it. So,
yeah, on one of your previous slides, I think since the 90% requirement for 90% accuracy and being able to determine which lane you are in and where within the lane you are, if you're not using cameras, how are you able to determine this just from the GPS data?
So as I talked about, whether our applications are dependent on absolute accuracy or relative accuracy, right? There are also other mechanisms to enable the accuracy of a particular receiver. There are proprietary mechanisms in terms of what can be done, how somebody can use a raw data, make a better judgment of what the GPS positioning system is. There are also differential GPS receivers that are available. So it's not that we cannot get very, very accurate positioning determination. We are looking at what cost, right? Can I spend a $300 GPS receiver to enable this 100% confidence level, or can I do it with a $10 GPS receiver, right? That's where the differentiation is. And I think this, the GPS, the new satellites are being deployed both with the GLONASS systems in Europe. So if you look at the roadmap of GPS technology in the next 10 years, it's looking very, very promising. So, I believe that these receivers are going to be very cheap, and we would be able to get very accurate location mechanisms in the very near future. Yeah.
Hang on just a second, please.
Will we be allowed to transmit other data?
We're recording this on the video, please.
Oh, okay. Yes, will we be able to transmit other data besides these basic safety messages? Say you have a caravan of vehicles, you want to use it for communications, sharing a radio station or something?
So the definition of the basic safety message is standard. There are other applications you can build. I mean, if you look at the 75 megahertz of channel, one of the channels is mainly used for basic safety message. Nobody's allowed to be mucked with it, right? Because we don't want people to go and change the contents of the message or add anything that's required. Because there's a lot of, so the basic safety message would not be user modifiable, right? But there are other channels that are available, because when we have 75 megahertz, we have 7 different channels, right? You can build applications to write whatever you want on the other side channels to be able to have, cars to communicate with each other and come up with any type of application that you want. But it cannot be piggybacked with the basic safety message.
Is there any meeting to assure the interoperability of the radios? I mean, what kind of is a car manufacturer getting together to test the interoperability?
So it was mentioned as part of the consortium, the Vehicle Safety Consortium. So the safety consortium has about 8 car manufacturers today, and they are inviting suppliers to work with them so that they could test interoperability of these different suppliers.
So the CAMP is the name for
Yes.
okay.
Yeah, the CAMP is the name. It stands for Crash Avoidance Matrix Partnership.
So in the video, they made a point of saying that the communications were anonymous, didn't include driver's license or license plate or anything like that. And yet some of the other slides talk about doing things like toll taking and things like that. There's clearly a tension between you can't be anonymous and collect road tolls at the same time.
What we are saying is the mechanism on how the toll gets collected is not based on what's in the message. It's the purpose of, can I have an application sitting on my hardware which talks to infrastructure and communicating with the sum of centralized server through 3G mechanism, right? To tell them that, okay, I've already been here and this is the message that I'm sending you, this is my position mechanism, right? It's nothing to do with, the safety aspect of the applications or the data that is coming out of it. As I mentioned, you can write any application that you want, but nothing based on the basic safety message itself. So if you are building a toll application, you would not be piggybacking coming out of the basic safety message. So you have to have a roadside unit which says, I am going to provide you a service called toll service. Then you go into a side channel and then, exchange whatever message you want. It can be, your subscriber identification number from your cell phone. Doesn't matter what it is, right? However way they identify you as a consumer that they can collect toll from.
I want to back up a little bit to the DGPS. I don't think a lot of people understand that means you have to have ground-based transmitters. When you have the instrumented intersections and signals, is that the plan to also put in DGPS units, or it's going to take an extensive deployment for me to feel confident that you can do sub-meter even with a 40 satellite constellation? I just don't see it.
So Federal Highway Authority, this is one of their major research topics. So they're funding, different aspects of this, how the GPS information can be improved. So you have differential GPS receivers, right? What's missing is the communication to the consumer, to the onboard unit about the corrections that need to be made. So one aspect is by instrumenting the intersections with roadside units that can send these corrections through the DSRC radio. But that doesn't preclude any onboard unit to get these corrections through FM channel or an AM. There are many mechanisms that are available to get these corrections. Instrumenting the roadway is one mechanism to be able to provide these corrections at a cheaper cost, right? If I have to have a 3G radio to be able to connect to the internet network server, then these corrections can come at a much rapid, right? So it all depends on the mode of communications and how these corrections are coming to the consumer and at what cost, right? Or if they are needed, in some cases, it's not required. As I talked about, we are building these applications with relative accuracy, not absolute accuracy. In some applications, it absolutely makes sense to have, a very accurate positioning systems. So it depends on what type of applications, in what scenario would we need these corrections, and at what cost are we able to provide to the consumer. Yeah. Yeah.
So what I'm wondering is the GPS errors. To a certain extent, they're all the same. Like two cars, one following the other, will see the same position, which with the same error, and that should be perfectly okay, right? Because they know their relative positions. They just don't know, are they 50 feet to the right or the left?
That's right.
I know I'm 50 feet behind that car in front. I just don't know.
For some of these signals, they'll need lane information.
Yeah, that's why you need the instrumented map information of the intersection.
No, that's not true. That's not true.
Okay.
You should be able to derive the lane information if you have enough cars traveling and they share that information, right? If you got 3 cars wide going down if you got 100 cars going along, I don't know if you're going to see 100 cars, and you see 3 tracks averaged out of those.
If they're keeping memory from, I don't see that flowing forward. I just kind of, again, skeptical that they're going to be able to track that much information.
So I can tell you, without requiring differential GPS receivers, we are able to deploy a lot of these applications and prove that they work very well, right? But I can tell you that we haven't had enough coverage as well, right? We don't know in urban canyon scenarios, in different types of mechanisms, how these applications work. I don't have the data, and neither the government or the people who are doing the research. We don't have a lot of data that we are able to collect. This is the purpose of the pilot that we are doing, is to actually run these applications in an urban environment to determine such scenarios, right? So it is possible that, when we start deploying this technology in, let's say, New York, downtown, Manhattan, right? We would require a lot of these corrections that need to be come in, but we don't have the data to be able to determine there are simulations that we have done, there are mechanisms that we believe that what needs to be done, but we really don't have enough data to be able to prove what is required to make it work everywhere.
Right. But they actually just said something there that scared me. I hadn't thought about before. In New York, can you get a decent GPS signal on a street corner in Manhattan?
So, it's like the GPS receivers definitely got better, right? It depends on, what sort of, algorithms that you're running, what mode you're running it on. So, your navigation systems work just fine in any place in the country, right? It's, navigation systems are not a very good example for active safety platforms, but that at least tells you some indication in terms of when a very good, known accurate position, that you can make certain predictions about, relative corrections and things. But I don't know if that's good enough for these applications to work. So.
Can I change the topics entirely and ask a different question? Do these devices, is it likely that these devices will have an API that allows, and the necessary communication support, that allows external software to get information from them, let's say third-party software, to do clever things?
Yeah, that's part of what we are doing is, we provide an API to a lot of the OEMs that work with us, and then, we enable a lot of applications. The purpose, I think, would be, as I talked about, safety, mobility, and environmental applications. So, I think it has to be opened up. It has to be, enabled to write all sorts of applications, as long as it doesn't, undermine the basic reason why these devices are built, which is to provide safety. And as long as the application developers are not allowed to muck with that, so there are sort of kind of a quarantine security mechanism that we have to provide as device vendors to ensure that that's not compromised. But absolutely, the intent is to ensure. I don't know if when the car manufacturer is actually deployed, whether they would provide it or not. But to me, that would be the intent.
Okay, thank you.
I was curious if you have a URL or something for more details about the protocol, so we can see how, for instance, the security system is going to work, so that it provides privacy, yet you can revoke the certificate of certificates of bad actors and just kind of get all the details?
If you look at the IEEE 609.2 spec, that would be a good start. It doesn't talk about a lot of the mechanisms in terms of how you interact with the certificate authority and things, because that's like a definition that we are working out, working with different suppliers, because that's not part of a real standard yet, how the communication needs to happen. But the actual security mechanism is part of the IEEE spec, which I think just became a standard now, so you can buy from online.
So it's 8211P?
No, it's IEEE 1609.2.
So I'll just quickly comment. I have an excellent technical paper from John Kenny of Toyota that's really an encyclopedic discussion of this topic. And if you remind me, I'll post it to the website. I should have done it before, but I forgot. And also, I believe our January speaker will probably be Christy Dudley from Santa Clara University Law School, who's involved with a currently open Department of Transportation request for comment that's actually on this topic. So Christy is involved with a group of, she's a consultant to some of the people who are actually formulating this standard. And, the European bodies are also in a similar stage. There's also it's either IETF-ITS or ITS-IETF mailing list, whose email address I have. And a lot of the heavy hitters from Europe, from SAE, from IEEE, and so forth are all on that mailing list. So anyhow, now if you're interested in networking and privacy and security, it's a really good time to get involved in this topic, because
I agree.
The standards bodies are really seeking intelligent comment and input from people in the community who know more about security and networking. So.
Yeah, you had a question?
My question was this, see all this way to provide the data, and you said the backend collects it, right? There's one, there may be tons, many backends, right? Because depending on the geography of interest and things like that. And do these backends talk to one another, or how do you envision this? Or is there something already there, or someone needs to build it?
Can you repeat the question?
Yeah, the question was, how do we envision the backend, data collection process needs to happen? Is it one server, or is it scalable to many sort of servers? How does it geographically, scale to every part of the country or the world? As I told you, currently there are models exist how people collect weather data, sensor data. There are, it's not going to be. It's already solved mechanism, right? The data collection backend, server.
Who owns this data?
It depends on who is collecting the data.
To the vehicle which is generating it, or it's the collector, they own it and they make money out of it?
So actually, that's a big discussion topic about who owns data. Whether is the consumer who bought the car owns the vehicular data, it is the OEM manufacturer who made the car owns the data, or is the government who collects. So there's a lot of discussion about the ownership of the data collection itself.
Can
and
anyone collect the data?
If it's in the air, I think you can, sure. You can come up with a mechanism. If you are Google and you have a lot of money, you can come up with sensors and receivers that you can put up and collect this data, and it's, once it is in the air, I don't think anybody is precluded not to collect the data.
Well, that's the legal situation has a lot of anti-snooping provisions already. You can't use a scanner to listen to cell phone conversations, for example. It's against the law.
Okay. Yeah, I think there you go. Well, it depends on it's a license ban and what the regulations that go with it and what's legal and not legal. So yeah, yes. Yeah.
I just want to mention too that they could triangulate off of each other's position for the radios in addition to the GPS if you wanted more accuracy and positioning.
Absolutely, yeah. The radios.
Please repeat the question.
Yeah, the question was, can the use of the radios be used to improve the determination of the position accuracy? Yes, absolutely. Yeah, the radios can be used, to improve the information coming from the GPS receivers. We talk about the radios or V2V radios. Yes.
You get down 1/10 of a meter or so.
Yeah. Right.
So Ravi, is there a discussion beyond the basic safety message and the channel that it will be assigned to of commercial use of the 802.11p?
The 1609.spec talks about 2,000 application scenarios. All the way from McDonald's sending advertisements to the vehicle, to all types of applications that they come up with. So I think the question of applications is the easy part to answer when you have the road that's already paved with every car that has a common radio, right? I think that the hardest part is to determine how long does it take for every car to have the same radio or the radio that speaks the same language. I think that is the definition, right? But what type of commercial applications can be developed is, I think it depends on who maintains infrastructure, where this infrastructure, where this information is being provisioned, and how this information gets to the consumer.
So one other question would be, with the pilot that's going on in Ann Arbor or the SimTD, are trucks and fleet cars involved in that at all, or is it simply passenger vehicles?
There are, out of this 2,700 vehicles, there are 2,400 passenger vehicles. There are some trucks, but not related to the fleets, right? Remember that this technology is not integrated with the telematics platforms yet. It's just, it's just doing its job on its own. So we can't compare it with the probe data or the telematics data that's already deployed yet. The trial is mainly focused on about this technology, and in the US, it's primarily on the safety purposes.
Isn't there 3 integrated trucks in safety pilot also, Ravi?
Yes, there are 3 integrated trucks, but we are not integrated with the telematics platform of the truck. It's mainly used to ensure that, yes, this technology or radio can be deployed on a bigger vehicle like a truck. That's the whole purpose of using a truck or a bus in there. It's not integrated with any types of existing hardware platforms that's part of the truck or the bus.
I think it'd be interesting technology for ambulances and
yeah.
fire engines to have.
Yeah, absolutely. And we have a trial or a test bed focus in that area. A question?
Is there any mode to relay the message? Through the radio. Let's say there's 3 cars, and can message be relayed?
Relayed. So the question was, can this message be relayed across multiple number of cars? The standard does not define that this is a mesh technology and the messages can be relayed from one another. We are not creating a multi-hop network here. The goal of this technology is only to have a broadcast scenario, and the messages are only determined to a single hop. You can come up with any other type of application or a protocol that relays this message from one car to the other, but that's independent of this technology or the radio spectrum.
Yes, I was wondering in terms of the geolocation, if anybody's actually looked at pseudolights as an alternative to differential GPS.
Yes. This is part of the Federal Highway research, that's going on to use the pseudolights as a mechanism to improve GPS accuracy.
Could you just say what pseudolights are?
So pseudolights are mechanisms, just like the geotransmitters that are available, depending on, where these transmitters are set up. It basically mimics a GPS base station. Am I right? Yeah. It's like a terrestrial GPS satellite, that it sends out GPS information from a terrestrial location and stuff, relying on the, but that's more accurately determined. So there are different types of
pseudo
But
lights.
it's a differential GPS transmitter.
Right. It's a differential GPS. So it determines, a lot of these pseudo lights are currently used for automated agricultural, like if you are a huge farm of land and if you have, these tractors that are used to tilt the land, and these GPS receivers that are dependent on the pseudo lights is used to accurately determine their position within that agricultural land. So these technologies are commercially available. You can buy service from them. It's integrated into these, commercial tractors for automated farming. So, it's not...
My question, though, is are they going to end up on traffic lights? It kind of makes
sense. Yes, it does. But it is cost associated with maintaining them, and, that is the whole purpose of this.
So it's getting to be almost 9 o'clock. I think we should call the formal proceedings to a close here. Please feel free to take some of the large amount of leftover food that we have. Please feel free to hang out a little longer and chat. I'm more than happy to wait until everyone is ready to leave, but I think we should release people who need to go to the bathroom. I'm told if you do go out this door, you may get, there's some doorways here that are locked now because of the building security. So if you get locked, just make a loud noise and I'll come and free you. Yeah. Thank you very much, everybody, for coming and for your participation. Please consider coming to the November 1st Android event with General Motors. It will be in Santa Clara next month. Or, as I said, probably we'll have an NVIDIA event in Santa Clara in December. So thanks again, and thanks very much to Ravi for a fascinating and professional talk. And I'll try to post the URL of the video from this presentation, the DOT camp video he showed, and the Toyota paper about DSRC as well.